Let's look a little bit more into the bonding in aldehydes and ketones, specifically at the carbonyl, carbon and oxygen. I copied over this information from a previous video just to again remind us that we have an electron deficient area at the carbonyl carbon, an electron rich area at the carbonyl oxygen. Also in a previous video, we drew this structure or this representation of the carbonyl where we're looking at it in a horizontal view. So one of the single bonds from carbon is away from us, one of the single bonds coming towards us, and then carbon to oxygen is in the plane of the paper. Now, carbon and oxygen have a pi bond between them, so we can represent that as the unhybridized p orbitals on carbon, unhybridized p orbital on oxygen. They overlap with one another. Let's use different colors here. They overlap with one another, and this gives us that molecular orbital. So we're going to talk a little bit more deeply about that molecular orbital here. And we will draw the MO diagram. And we're just looking at this p orbital only. So really what I'll do here is copy down that atomic orbital representation. We show all of the bonds, and then we show that carbon has an unhybridized p orbital and oxygen has an unhybridized p orbital. So we have two p orbitals. That means that we will have two molecular orbitals. One will be higher energy, one will be lower energy. The lower energy p orbital is the one that results in a pi bond where we have both p orbitals in phase with each other, and we have bonding occurring in the overlap of these two p orbitals. So here we have a pi bond, and then if we switch the orientation of one of these p orbitals, we then have a pi star or an anti-bonding orbital. This is the higher energy orbital. I'll keep one orbital drawn as we have drawn them with these colors, and then the other orbital, we've switched the phase. I'll start coloring in the blue orbitals here just to make it a little bit more clear. When we have the same phase overlap, that's our pi bond. When the phasing is opposite and they cannot overlap, that's a pi star. In this pi bond, we have two electrons. We have one double bond. So in the pi bond, we have two electrons. We show them in the lowest energy orbital. Let's just emphasize this here. We have two electrons in the pi bond. We started with two p orbitals, two atomic orbitals, and we end with two molecular orbitals. And that follows the rules that we talked about early in the semester, that for however many atomic orbitals you start with, you should have the same number of molecular orbitals, and that's what we have. So here's the MO diagram for that carbonyl carbon to oxygen pi bond. Now this pi bonding orbital is full. We have two electrons in the pi bond. So let's describe what happens when we have a nucleophile reacting with that carbonyl carbon. So the pi bond is full. we'll say the pi bonding orbital Now we're going to talk about nucleophilic addition to these carbonyls. And so when a nucleophile, which we'll abbreviate as Nu, with electrons and a negative charge, not all nucleophiles have a negative charge, but we will represent it that way here. So if we have a nucleophile that reacts with the carbonyl, now, before I go on here, let's think about where a nucleophile would react with the carbonyl. So the nucleophiles by definition have electrons that they are willing to give away and share with an electrophile. So if the nucleophile has electrons, I'm going to scroll back up to where we're describing electron-rich and deficient areas in the carbonyl. The oxygen is already electron-rich, so that's not looking to accept any new electrons from a different molecule. The carbonyl carbon is electron deficient. So if we have a nucleophile present, it will bond at the carbonyl carbon. Because the carbonyl carbon is electron deficient, and nucleophiles have electrons they're willing to give away. So when a nucleophile reacts with the carbonyl carbon, it adds, now thinking back to this MO diagram, it adds electrons to the pi star orbital. And I'm going to do a dot, dot, dot right here. We'll finish the sentence after we draw the MO diagram after having added a nucleophile. So I'm going to copy and paste what we've drawn so far here. If you're not able to copy and paste your notes, you might just take a moment and redraw that MO diagram. You want to have 2 electrons in the pi bonding orbital. That's where the electrons in a carbonyl bond would exist. So now if we have a nucleophile present, a nucleophile has in some orbital, it has non-bonding electrons that will then overlap and be shared with the p orbitals in the carbon to oxygen bond. So when that occurs, when the nucleophile reacts with the carbonyl carbon, it adds electrons to the pi star orbital. So if we're adding electrons to the pi star orbital here, right there, we have now 2 electrons from the nucleophile. Now we have the same number of electrons in a bonding orbital as we do an anti-bonding orbital. So when this occurs, the pi bond breaks. So here's the rest of the sentence. Bond order is equal to 0. So when a nucleophile, a molecule with available electrons, reacts with the carbonyl, it will react at the carbonyl carbon because that's the electron deficient atom. It will add electrons to the pi star orbital in the molecular orbital diagram because that's the only location where additional electrons can exist in this bonding orbital. As that occurs, we have the same number of electrons in an anti-bonding orbital as we do a bonding orbital, and so this pi bond will break. So when a nucleophile reacts with carbonyl carbons, the carbon to oxygen pi bond breaks.